So here's the problem. You've got you got a cat. And you launch it with velocity v naught, all right? And then, of course, you put a bomb in the cat. I mean, why not? And so up here, the cat explodes. All right. So imagine the cat explodes at the very top of the flight. Exploded. All right, so, and we can do some stuff. I mean, let's say that this is, I don't know, 40 degrees. And suppose the initial speed is, I don't know, 1,000 meters per second. And then this is where I get into trouble when I make up this problem. It's very easy to give velocities to the fragments of the exploded cat, which are physically unreasonable. And not in the sense of the technical problems that are intrinsic within putting a bomb in a cat. I'm not really concerned with those details. I mean, you can sedate it. Surgery's not that hard. Or don't. I mean, I don't know. It's a cat. But I don't know. I got to come up with a reasonable. And so then I need something kind of. I think if I do this, I can make sense of it. Well, I reserve the right to change this. Suppose that this is going down. After the explosion, this part is going down with, let's say, 100 meters per second, straight down. And that has half the mass of the cat, all right? This other one has the other half of the mass of the cat. It doesn't matter how much mass that is. The question then is, I don't think it does anyway, how far does the top half of the cat go? So then the question is, what's that? No, I said all I'm telling you is that the bottom half goes at 100 meters per second straight down. The explosion is such that that happens. We can't. In fact, that would be physically impossible. All right, so this is not a closed system. The net external force is not zero, right? I mean, you could model the explosion like a collision, all right? But, well, no, you can't. I'm sorry, I'm an idiot. Let me shut up here and just start working it. So the initial momentum is what? We've got the mass times the initial velocity, right? So that's the mass times, v naught times what? You got yourself a cosine 40 degrees and a sine 40 degrees. What's the net external force? If you think about any stage in this motion, the net external force is the same. mg, right? That's the external force, gravity. To be more clear, what we have is that the external force is equal to 0 minus mg, right? Now that's equal to dp dt here. We're thinking of the cat as a system. because we know the cat has two halves, right? So eventually the lower half of the cat will be M1 and the upper half of the cat will be M2, right? What can we say though? So this is also what? This is like dpx dt, right? dpy dt, right? So what do we get to say about the x component of the momentum? Right? Now, the process of the explosion, I guess, well, how to say this? Oh, let me stop talking. All right, so at least from here to here, what's the net momentum? Right before the explosion, the net momentum is what? So px for the intact cat is simply mv naught cosine of 40. Momentum in x direction of unexploded cat. Unsploded. It's constant, right? Because there's no force in the x direction. The momentum in the x direction stays constant. But how about the y momentum? What happens to that? What does gravity do? Minus mg, right? So it's decreasing the y momentum. But this, you guys know this already, right? This is just a kinematics problem, really, from here to here. So what's the velocity of the y? Vy is what? V naught sine 40 degrees, right? That's the initial y velocity, minus gt, right? How much time does it take to get to the halfway point? Oh, I'm sorry. I'm an idiot. It's easier than that. What's the y velocity at the zenith of the flight? Duh. Yeah. Sorry. I'm an idiot. So right here, right before the explosion, the y velocity is 0, right? So let's see here. So the momentum just before explosion is what? M v naught cosine of 40, 0, right? Now, if I actually told you the explosion wasn't at the zenith of the flight, if the explosion was at some other part of the flight, then you'd actually have to figure out the time and figure out how much y velocity, how much y momentum it had before the explosion, right? You could, in principle, work a more complicated problem like that, but thankfully for us, it happened at the zenith of the flight, where the y momentum is 0. So there's that, right? Now, before or after the explosion, momentum is conserved. All right? I mean, this is useful if you're studying explosions, right? If you find that one fragment of the bomb went that way with a certain amount of momentum, another part of the bomb had to go that way with that same amount of momentum, or some conglomeration of pieces of the bomb had to go that way with that. The net momentum before and after is 0, right? Assuming the bomb is just sitting there, right? So you can't have a bomb that just goes one way and not another unless you've got some kind of something that can, well, anyway. In order to make it directed in one thing, you have to have some kind of really large mass, right, that is very, very hard to move, so that, well, anyway, I digress. So this is equal to what? This is equal to, well, on the one hand, m over 2, right, 0, minus 100, meters per second. This is the momentum of the lower half. And then what? Plus what? Plus mass of the upper half of the cat. And then you've got some, let's say V1. Right? We'd like to figure out what that V1 is. Once we know what V1 is, we can solve the range problem, right? By piggybacking what we already know from the zenith to the next thing. So, what is V1? Well, you can solve it, right? I mean, m over 2 V1 is equal to, apparently, mv naught cosine 40, and then m over 2 times 100. I just add this vector to the other side. I mean, add this up here, and then that isolates this. So I would get m over 2 v1 is equal to mv naught cosine 40 plus the m over 2 times the 100. The m's cancel, and you multiply by 2, you get v1 is equal to twice v naught cosine 40, and then 100. That's totally unsurprising, right? Some of you, if you understand momentum and collisions, you knew as soon as I told you it goes straight down 100 meters per second, the other one should go 100 meters per second straight up. And if you said that immediately, it's because maybe you already understood that the initial the y momentum before the collision was 0 there, right? If the y momentum before the collision wasn't 0, I wouldn't be guaranteed that the speed down is matching the speed up for the y, or if the masses were not equal, I wouldn't be guaranteed that matching. But it is, because they're equal. And so there you go, that's V1, which is what? (2000 times cosine 40), which is what? 1,532. I agree. 1,532 meters per second, comma what? Oh, 100 meters per second, yeah. All right, so this distance right here is what? Let me call this R1. R1 is equal to what? R1, we have a formula for that. That's 1,000 meters per second quantity squared times the sine of 80 degrees divided by g, right? That would give me the total range, right? V naught squared, remember V naught squared sine 2 theta over g gives me the range if I'm starting and ending at the same height. But I only want half of that, right? So I do divide by 2. So this R1 would just be that number, whatever that is. Whoa. It's 2 theta, though. Yeah, 50.25 kilometers. So the cat will be safely away from us when it explodes. Good. I mean, honestly, folks, this kind of velocity is like the sort of velocity you find in naval guns. The only thing you can really shoot at that kind of velocity is like solid chunks of metal. All right. Unless you had a metal cat. Or you could perhaps bronze the cat before. Sorry. Well, anyway, what's the initial y here? What's the formula for max height? We worked this out before, right? If you must, I could solve mg y naught is equal to 1/2 m v naught y squared. So it's what? It's v naught squared sine squared theta divided by 2g. That's the max y. I only use the y kinetic energy because it has the same x kinetic energy before and after. They cancel. 1,000 squared times the sine of 40 squared divided by 19.6. Whoa! 21.1 kilometers up. Man, that's something. Then what do you gotta do? Then it's just I don't have time to finish it obviously, but you just have to look at the equations. Y is equal to 21.1 kilometers plus 100 times time. That's the initial y velocity. Minus 1/2, well, minus, get to the point, minus 4.9 t squared, right? You set that equal to 0, find a solution. And then x, on the other hand, is equal to, well, fine, 50.25 kilometers, and then plus 1532 times time. So you solve that to find the time where that happens, and I guess I could figure it out. Just a second here. If you humor me for a minute. I'll end class early some other day. How about that? Sound like a deal? Oh, thank you. Yes, be wary. I should use, this is 21,000. Thank you. That is the danger of using kilometers. There we go. So, quadratic. My A is what? Minus 4.9. My B is 100. My C is 21,100. I get time of 76.61 seconds. And so if I multiply that, let me out. I'm stuck in the equation solver. All right, so then 5,250 plus 1532 times 76.6. I get, drum roll, 167,601. In other words, 167.6 kilometers. Or 100 miles.
At that distance, could you some factor in the curvature?
What's that?
At that distance, could you some factor in the curvature of the Earth?
Yeah, I think, yeah, maybe we should start to factor in the curvature of the Earth. And well, after the explosion. Yeah, that's the 76 seconds is that, I think.